Hello. Now we'll see that in case of conductor, what will be happening with the cavity? This is my cavity. So, and this is my conductor. So I'm having a conductor. Inside the conductor, there is a cavity. Okay. And I want to know what will be happening with the electric field inside the cavity. Because one thing is sure, we already learned that electric field in this region, wherever the free electrons are there, inside the conductor, there the electric field is going to be zero. Whether you put this in space or you put this in external electric field. Okay. Now, if there is a cavity, so inside the cavity there is air. So there is air. Because of that, the electron cannot move there. So free electrons are not available. There, no free electrons. Free electrons not there. Okay. Since free electrons are not there, I cannot say that electric field will always be zero here. Okay. So here we have to go for Gauss law. So if there is this cavity and inside the cavity if there is some non-zero charge, I'm putting the non-zero charge. In that case, there can be multiple charges as well actually. So to check whether there will be a electric field or not, I'll draw a Gaussian surface. This is my Gaussian surface. Gaussian surface. And for the Gaussian surface, I'll apply the Gauss law, that is E dot ds integration, and that is equals to q in upon epsilon naught. Okay. So if this q in is 0, if q in is 0, in that case I can say that this E dot ds will be 0. But in this case also I cannot say that since E dot ds is 0, but I cannot say this does not mean that E is 0. It does not mean that E is 0. We can only deduct that E dot ds will be 0 in this case. If there will be some sort of symmetry with q in 0, and if due to that symmetry I can take this E outside of the integration sign that as we used to do in case of Gauss law, in that case we might be able to say that E will be 0. In this case, this is a general case. There is no symmetry here. Okay, let's see this example. So if I'm having this solid sphere, and inside this solid sphere I'm having a spherical cavity. So this is my cavity radius is small r and the solid sphere is of capital R radius. Okay, and this is conducting material. So this is my conductor. Okay. In this case, this is my conductor. In this case, I want to see what will be the electric field. Electric field here will be 0. And since we are dealing with a conductor, there are a lot of charges. Okay, so we cannot outrightly say that there is no charges, so the field will be 0. There are a lot of charges, there are a lot of electrons, and these electrons can rearrange itself. In case of non-conductors, there were electrons there too, but those electrons could not rearrange themselves. Here they can rearrange themselves. They can form a dipole. That's why it's very difficult to say that E will be 0. But here, in this region, E will be 0 because this is a property. Free electron at steady state will make the electric field 0 in this region. And inside the cavity, if I want to see, I'll make the Gaussian surface. And if I make the Gaussian surface, then E dot ds integration will be equals to q in upon epsilon naught, and that is 0 because there is no internal charge. And since this is Gaussian surface is spherical, cavity is spherical, as well as the body is also spherical. There is a symmetry, and due to that symmetry, we can outrightly say if there will be a non-zero electric field here, that will be constant. Okay, so because of that, we can take this E outside of the integration sign, and that will be 0, and this leads to E 0. So you see, E is 0 only in case we were able to take it out, and we were able to take it out because there was a symmetry. Okay. But in this case, we cannot, this is not a general case, this is a specific case. So E might be 0, E might not be 0. If E is, this Q in is 0, if Q in is 0. But if Q in is non-zero. If Q in is non-zero, that makes E dot ds also non-zero. Okay. So if E dot ds is non-zero, then it means for at least one point in the cavity, I'm not saying everywhere E will be non-zero. I'm saying at least at one point E will be non-zero. Okay. So we cannot say, in this case I can definitely say that electric field is non-zero. Even for a point. Electric field is non-zero, but only within the cavity. So that is a property. So if there is a conducting body, and in that conducting body if there is a cavity, and if I put some charge inside the cavity, then due to this charge within the cavity, electric field will become non-zero. How to calculate that value? This will be a different case scenario. But due to this charge, field inside the cavity will be non-zero. Though you put the charge here, field will remain zero. Here, field might be zero, field might not be zero. Okay, but inside the cavity, field will not be zero. So that is one of the property. Okay, I hope you understood that. Thank you.